In this video, I'm going to briefly highlight 3 JLS features that students tend to overlook. Using these features will help your circuits look nicer and help you avoid unnecessary repetition. The important thing to remember is that the author created JLS specifically for the computer organization assignments he was using. If some part of an assignment was unnecessarily tedious, then he added a feature to make it easier. This means that if you find yourself doing something tedious or repetitive in JLS, you're probably overlooking a feature designed to make that task easier, and you should check with your instructor. Suppose we're building a 4-bit ripple carry adder. This ripple carry adder will have 2 4-bit inputs. And at some point, we'll want to break apart these bundles of 4 wires into 4 individual wires so we can send the input bits to the individual full adders. This is what the unbundler does, and in this case we use the single bits so we get 1 wire for each of the 4 wires in the bundle. But now suppose we're building a 16-bit adder and we want to build that by chaining together 4 4-bit adders. In this case our inputs will be 16 bits, and at some point we'll want to break apart this bundle of 16 wires into 4 bundles of 4 wires each. So again we'll use the unbundler, but this time we're going to use the group bits feature over here. And when we select the group bits, what we can do is choose which wires get bundled together. So here I'm going to put bits 0 through 3 in one group, 4 through 7 in one group, 8 through 11 in one group, and 12 through 15 in one group. And then you can see we have our 4 4-bit bundles. Notice how this is much easier and cleaner than ungrouping or unbundling all 16 wires and then rebundling them into packages of 4. The next feature I want to point out is the extend bits gate, or I like the tooltip better where it says make n copies of the input. This does exactly what it says. It takes 1 bit in and then you get n wires out that are all identical to that 1 bit coming in. One place this is useful is if you're building a multiplier. So let's suppose we're building a 16-bit multiplier. Now what we'll need to do several times through this multiplication process is AND all 16 bits of the first input with a specific bit in the second input. Let me create the second input here. So what I want to do here, for example, is take bit 0 of input B and AND that with each of the 16 bits of input A. So the first thing I need to do is be able to grab onto bit 0 of input B. Notice again I can use the group bits feature here to just grab that 1 bit I want. So I'm going to select group bits, select bit 0, and I only have to select that 1 bit. It's all I need right now. So I take these 16 bits and grab just that 1 bit. But now I need 16 copies of that 1 bit, one for each of the wires in A. So I'm going to select my extend bits feature here, and I want 16 bits of output, and I can connect that up. So now I have 1 bit coming in and 16 bits coming out over here. Now I want that ANDed with each of the bits in input A. I can do that all at once by choosing 16 gates here. What that effectively gives me is 16 AND gates all stacked up on top of each other. And so now I can apply that to both input A and the extended input B. And I can do this all in one step as opposed to having 16 individual AND gates, which obviously would be very tedious to put together by hand. Another place that this extend bits feature is useful is when you're extending a signed integer, let's say from 16 to 32 bits. Finally, let's look at named wires. So for the most part, when you're building a circuit, you want to see all of the wires because they show you how the components interact and how data flows through that circuit. One exception is when you're building a CPU and you have a clock and a bunch of registers. So let me create a few registers here. Now we can certainly connect the clock to the registers explicitly, but when you're building a complete CPU, what you end up with are these clock wires throughout the circuit. They don't add much clarity to how the circuit works, they just kind of clutter up the diagram. So in this particular case, a better way to do this is to use named wires. So over here I have this button here with the arrow coming out, and I'm going to create a wire creatively named clock. And notice how it kind of disappears. And then when I want to connect the clock up to the registers, I push the other button with the arrow going in, select clock, and I can connect that to each of my registers. So now the registers are all connected to the clock without the wires strung out throughout the circuit. Now be careful, this feature can certainly be overused. What I don't want to see as an instructor is a bunch of components dumped randomly on the screen with named wires with no feeling at all for how the circuit works. But a few carefully chosen named wires can make a circuit much easier to read. So I hope you find these features useful and that they help you save at least a few minutes throughout the semester as you work on your projects.